All right, so let's get started, everyone. We are switching topics in the class and going to start talking about clustering. This will be kind of one of the four main kind of approaches to data analysis we'll be talking about this semester. It's another one of these unsupervised methods. We're not going to have labels on the data. We're going to find the structure that is in the data set inherently, and but it's going to be different than the structure we found using dimensionality reduction. Okay, and there are lots of types of clustering, lots of formulations, and frankly, it's not clear why one is necessarily much better than the other. There are also lots of versions of classification, which we'll see in the next section. But in classification, you're going to have labels, and you can kind of test them against each other because it matters how well they do on the labels. With clustering, you have to define some sort of cost function, or some sort of objective that you're trying to optimize, and you get to choose what that objective is. And because you can choose it, then these different types of clusterings are not necessarily so comparable to each other. So this has given rise to lots and lots of variations of this. We aren't going to talk about all of them. In this course, we are going to pick out what's probably the singular most common version of this, the often called k-means clustering. And that's what the point of the lecture will be on. Tuesday, that specific algorithm associated, or the core algorithm associated with that, and kind of how to think about that problem. But kind of more generally, we'll think about this thing called assignment-based clustering. And what we'll do today in class will mostly be talking about, okay, what is the formulation of assignment-based clustering? And so we'll see again, we're going to get to something that looks like the sum of squared errors again, but the structure of it is going to be different. And so we'll mostly be looking at the structure of the problem today. And then, if you go to the schedule, then on Thursday, the third lecture in this section, we'll be talking about kind of an extension of k-means to mixture of Gaussians. That'll mostly be what that lecture is about. And this is kind of a neat extension of it that does kind of two things. One, it kind of relates it to kind of the stuff we talked about in dimensionality reduction, where we're thinking about kind of high dimensional subspaces and kind of how to reduce to that. And it also goes back to when we thought about the probabilistic modeling, and we're thinking about likelihood functions. And so kind of the k-means of formulation is kind of a simpler, fairly easy, I think, to understand discrete formulation. But kind of to model it data more generally and powerfully, this mixture of Gaussians is kind of like the right way of doing it if you have enough data to actually kind of fit the slightly more complicated models here. Okay, so that'll be the plan for this section. And okay, other important thing, quiz 5 is today. So we'll stop the lecture around 10:35, probably maybe a bit early, and we'll have a chance to take the quiz here in class. And then also homework 4 is due next week on Tuesday. Again, homework 4, kind of like homework 3, is going to be a little bit more kind of pushing the boundaries of what you guys are, exactly what we did in class, what I'm asking you to do. And it's going to have it's got the two parts. One, the gradient descent to do linear regression, which is kind of a synthesis of ideas, and then the dimensionality reduction, which I think is conceptually one of kind of the more challenging things in the course. So don't wait until the last day to do homework 4. Use the so the help hours and ask questions on Canvas discussion board. There's already been a lot of good discussion, so your questions might already be answered there. So thank you for those of you who had questions on there. So great. Yeah. So okay. Any questions on the schedule, or should we just get into it? All right. Okay. So clustering. So what we're going to talk about today specifically will be this kind of slight foray into kind of computational geometry view of things called Voronoi diagrams, and this will help explain the kind of the underlying geometry of assignment-based clustering. But first, so what is clustering? What is clustering? This is like every other one of these four topics: regression, dimensional reduction, classification. There'll be kind of much more straightforward answers of, what the answer is, to questions kind of like this. Clustering, it's more ambiguous or flexible, but let me try and give you a general sense. We're going to have n n objects, okay, and in this class, okay, well, we're going to say that this is going to be a let me make sure I fix with the notation we're going to use later. Yeah, so this will be a set set X, and we can think of it as X1 up to Xn, and this is a subset of our D. Okay, so we'll think of these as points in some d-dimensional space. These are vectors, right? Input d-dimensional vectors, a set of n of these vectors. But in general, it could be other sorts of objects, right? And if you look in the book, and you take in the data mining class, we'll kind of think about this more generally. The other thing you have is a distance function, d, which goes from, let's just say from x to the real values. Okay, so the real values, which is positive, takes in two values and says how far apart they are, right? And so this class, again, we're going to have that d of xi, xj is just going to be the Euclidean distance xi minus xj. Okay, so our typical straight line distance between vectors, that's what we're going to use as the distance. Okay, but in general, again, you can use other distance functions for a number of the formulations. Actually, for k-means, our main thing that we'll talk about, you basically need the Euclidean distance for this to work. This is the most common thing, but other algorithms can use other distance functions. Okay, so this is the input, and the goal is to let's say group the objects into k sets. So one, objects in the same set, these should be close, and I'll measure close using the distance, and the objects in different sets, I want these to be so far. Okay, so if objects are similar, are close to each other, they should be in the same set, or if they're in the same set, they should be close. If they're in different sets, then they should be far. Okay, so kind of a very simple two-dimensional example of this might mean that I have kind of, if I have points, I can draw in 2 dimensions, right? And I might think, okay, these blue things, these are, x1, x2, x3, and so on. And I'm going to find 3 sets, right? So set 1, set 2, set 3. And I want to say, okay, these are all close to each other. In set 3 and set 2 and set 1, they're all close internally to each other. Right, so kind of there are 2 objectives here. If the things in the same set are close, that means these distances in between objects are small. And then the other objective in different sets are far. That means these edges in between the sets, those edges, those lengths are kind of far apart from each other. Okay. Okay. Right. This is kind of vague. This encapsulates most of clustering. Not even all of clustering follows this pattern, but this is a pretty kind of abstract idea of what's going on here. If your data set looks like this and you have points in 2 dimensions, and you run an algorithm for k-means clustering, it's going to work fine. In principle, you're better off actually. Often what I would suggest doing is to plot the data and then draw circles around the clusters. If it's in 2D, draw a picture and then just circle things. That's going to work well, and you'll know it works well because you're seeing the actual data. But we'll see algorithms that will kind of automate this. Yeah.
Measure for how well vectors fit into like cluster model, kind of like the innocent fit for regression.
There's like people use like this R² for regression, for instance. There are formulations for this. We will talk about the k-means objective mostly in this course, and that will give you some measure that you'll be able to say, here are 2 ways I could cluster, which one has a lower score, and we want to find the one with the lowest score. So we will use this general approach. There are other sorts of score functions you can come up with. I will give a sense of some of those, and there are many others that are even stranger. Maybe I'll give a little intuition into some kind of how much variety there is in the space, as we in kind of the last lecture in this sort of section. Yeah, so I will get to a mathematical formulation, but I kind of didn't want to quite get there yet. I want to mention this is kind of an abstract thing. Okay, my kind of view on clusterability is that, okay, I pre-wrote this up, it's a little wordy, but when data is like easily or so naturally clusterable, like the data objects are naturally in kind of tightly packed clusters and they're separate from each other, whatever your objective is, then actually most algorithms work well and work pretty efficiently. When data is not easily naturally clusterable, then pretty much no algorithm is going to find good clusters. There might not be clusters in the actual data. There's a lot of, I taught the data mining class here for many years, and there's a lot of data sets, and you have in there, you do like a large sort of project on data that you choose yourself. And people came with data and said, I want to do clustering on it. Let me try a bunch of these algorithms. And a lot of times, a very common type of data look kind of like this. And I would call this like, a smear of points, where there's kind of this, dense here, and they kind of dissipate in density as you get further away from something. And they run clustering on this data set. And look, there aren't well-defined clusters here like there were in this picture here. Okay, there might not be well-defined clusters in your data. And if that's the case, you can try a whole bunch of different algorithms. They do very different things, and probably none of them are going to find good clusters, right? You can run them. They'll give you the best clustering algorithm, but it doesn't mean that there are clusters in the actual data set. Whereas if there are nice grouping of points, most of the algorithms work fine. There's some stuff on the boundary where, well, it's kind of clusters, but they're kind of hard to see, but I think they're really there, or maybe they're noisy. Then some algorithms work better than others. The k-means approach we'll talk about in mixture Gaussians are ones which are kind of very common, fairly easy to use, very, very popular, and the mixture Gaussians has a lot of nice kind of formulation behind it. So the k-means has a lot of nice kind of math underlying it. That between the two of those, I'd say 80% of what people mean by clustering is probably within those kind of k-means and mixture of Gaussians. So you're getting a pretty good sense. You kind of get another 15% in the data mining class, and the tail is very long. There's lots of kind of fancy, obscure things. Okay, so I won't spend a lot of time on clustering in this course compared to other topics, because I think clustering is probably, it's a very kind of attractive concept. You're like, oh yeah, I can find these different sort of customers in my data, in my customer base, and this will help me understand what's going on. And oftentimes there aren't clusters. And when there are, the simple algorithms so typically work. A lot of actually the variation within clustering, I would say, is the choice of the distance function. We're going to just use Euclidean so you see how stuff works in this class, but you can actually go from maybe a smear to a well-separated group potentially by choosing a distance function which is somehow informative in some way. But we're not going to talk about this in this class. This is kind of more advanced ideas. Yeah.
This might be a little beyond, might go over this, but if you like randomly shoot X and Y and put points, it will naturally cluster. How do you basically try to turn your human brain off?
Yeah. So if you right, so let's say I want to, I pick 0, 1, 0, 1, and I put down random points in here, right? You're saying,
and X and Y are uniform.
Yeah, so there's a uniform distribution on X and Y. It's what's going to happen, is that you're going to tend to find some points which are naturally closer together than you would expect, but you're probably not going to find something where you get big, kind of these very easily defined kind of groups of points that you can kind of draw circles around, and that the circles are separate from each other and all the points and the circles are small. That's kind of conceptually what I mostly think of with clusters. There are other forms of this, but this is kind of the most common way of thinking about it. And this is not what you expect to see, right? There's whole swaths I didn't pick, right? So I would say in general, this is true where you tend to get some points which are near each other more than you might expect, but you probably don't get whole like patterns like this showing up if it's uniform.
So given something like what you draw circles, if you had a little bit more dots spread around, but have like here's a small little grouping here, but there's some outliers away from that little circle.
Sure, yeah. Right. So if you had some points out here, but 95% of the points are kind of in these clusters, the algorithm should still work pretty well, right? K-means, the algorithms for K-means work pretty well. Mixture of Gaussians will actually be pretty natural for this, and we'll see that, right? Mixture K-means it'll be easier to understand. The most common thing, mixture of Gaussians will put kind of a probabilistic flavor on top of this, and it will make sense. This is when actually there was some phenomena generating these clusters in this way, and this actually does arise. Doesn't always arise, but it certainly sometimes does, and these are kind of the right algorithms for it. Yeah. Oh, using something like non-Euclidean.
Yeah.
Yeah. Okay, so yeah, so this is a great question. The answer, you have to step back a little bit. Okay, when I say, okay, your data your data objects are d-dimensional vectors. Well, your data objects don't usually start as d-dimensional vectors. There's this whole step that we haven't really talked about very much in this class, but say the data mining class will get much more into, of how you go from some things you observe, some raw messy data, into vectors that make sense, right? And so you go to vectors because of most of the algorithms, like in the data mining machine learning libraries, take those vectors as input. So you want to convert into that, and then you can run all your built-in algorithms. But how you do that is a modeling choice. And sometimes you go back and say, look, I don't want to use Euclidean distance. I want to say, okay, that I'm doing clustering on like some documents, or on like some images, or on like some strings of text, some tweets. Which tweets are more similar to other tweets? Well, there are ways to kind of convert this into Euclidean distance, but sometimes those aren't the right things to do. You can use like an edit distance between words. This does not map well into Euclidean distance. In fact, it's known that you can't do it without a lot of distortion. But it's kind of a right way to measure distance between words. And so you have to use that distance natively, and sometimes you don't use the Euclidean structure in the clustering algorithms. We won't talk about those in this class. And so maybe there's one I will mention that can be used in that way, where you only need to, the only way you interact with the data is you measure distance between 2 points. But you don't need to actually be able to draw it or embed it into some space. Now, what you could do is you could take another distance, like remember with the distance metric learning, like the distance between 2 airports. And that's my distance, and I want to cluster them. And what you do is you start with DML, and you embed it into Euclidean space, and then you can use the Euclidean distance. But I wanted to start with a different distance function. And sometimes you can just natively use that distance and skip the step of running DML. And there are slightly fancier algorithms you can use. So it kind of it's a really great question, and this class was kind of designed not to get into that sort of question a lot, but when you're doing data science, it's a very important thing to keep in mind.
Don't.
What?
So don't do it now.
Yeah, so we're gonna. My goal is to give you the basics of these things in this class, so you understand the mechanisms of stuff, and we'll use Euclidean distance, and you'll get it. It's more complicated to go beyond that, and so you can read in the textbook. Chapter 4 in the textbook, which we skipped in this class, is all about different ways of measuring distances, and there are lots of non-Euclidean things in there, and you can read about it to get a sense of that. Okay. Okay, so the formulation we're going to talk about is, so I want to write down my clustering, let's say like so cost function. And so this will be, so the k-means one, and we'll come back to this and talk about some generalizations of it. But we're going to be given kind of some data x and a value k. Okay. Yeah, so the value k I won't quite introduce first, but the cost on, say, x, and I'm going to say a set of clusters s, and I'll define, most of the section will be defining how to think about this, is going to be sum equals I equals 1 to n, the sum over all of the data points. and I'm going to do xi minus a projection onto the clusters in some way squared. Okay, so this is what our kind of our cost function is going to look like. I'll call this kind of the two cost function, and we want to somehow kind of find the best S. S is going to somehow define the clusters, and this should look basically the same formulation as the dimensionality reduction problem. A sum of squared errors with the projection somehow onto some object, right? In dimensionality reduction, that object we wanted that to be a low dimensional object, a low dimensional subspace. That was our goal. In clustering, it's going to take a form which is going to be so different. And in fact, I'm going to change this, and we're going to actually use a different notation, but basically the same thing. We're going to use so phi of x. That's supposed to be a lowercase phi. So this is going to be kind of like a projection function, or it's going to be a projection function, but it's going to take a form which is so going to be different. Okay, and let's see, and our S is going to be a S1 up to Sk. This is where the K parameter comes in. This is going to be set in our D. So this is going to be a set of K sites, which are basically points in our D. Okay, so I'm going to get a set of, say, sites, S1, S2, S3, S4, and in this example, 4 equals K, the number of sites I have, and I'm going to project all the data onto these, right? So I'm going to have kind of data points, okay, and I want to project them onto these clusters, right? And so this projection function, phi of S, is going to project onto these. Okay, this is kind of what the answer is going to look like. Okay, where every point is projected onto what's the closest site. Okay, so this project xi onto the closest Sj in S. Okay, so this is the main idea here. I should have drawn this in red. Okay, so I want to project all the data points onto the closest site. Okay. I mean, very similar to what we did with dimensional reduction, except that was projection onto the line. We could solve that with, so like a dot product. We can't just solve this with the dot product. It's not a linear thing here. And so that's going to make this a lot kind of harder to kind of solve and work with. Okay, so what I want to talk about for the next bit of the lecture is the structure called a Voronoi diagram, which is going to describe what the structure of this projection. And this will play kind of a key role in kind of understanding how the k-means formulation and all assignment-based clustering algorithms sort of, which fall in this sort of category, kind of how they work or what they have to deal with. Okay. So Voronoi diagrams. Okay. So we'll say for a set S, which is going to be a subset of our D, and the size of S is going to be equal to K. These are going to be some sites. And this is basically the structure of phi of S, which is the going to be arg min of Sj in S of X minus Sj. Okay. So this is actually the same, that statement's actually basically the same thing as the projection we did in dimensionality reduction, except S is now a discrete set, where before we were doing the arg min onto a low dimensional subspace, and we could do it with just dot products, kind of gave us the answer. But now we need to look at the structure, okay? And yeah, let me first describe this just in a one-dimensional picture. Okay, so I'm going to have S1, S2, S3, and S4. And I want to know what part of the space, what the Voronoi diagram tells you, okay, is, and so this is, there's some underlying line here. This is where D equals to 1. So this is R1 here. And so what part of R1 maps to each Sj? Okay. Okay, and what we can do is what we can kind of draw these, so bisectors, okay, these bisectors between, in this case, the consecutive points, okay, and so then the Voronoi cell, can't write today, cell of S3 is going to be this region in here. It's this one-dimensional region, okay? All these points in between the bisectors, their closest point is going to be S3, okay? So if I have a point X here, its closest point is S3, okay? And so that's what the structure looks like here in so one dimension, okay? This kind of makes sense so far. If we go to 2 dimensions, in R2, okay, things start to get more interesting here. Okay, let me draw a little bit larger example here. So we have S1, S2, S3, S4, S5, S6, S7, and S8. Okay, I want to draw this Voronoi diagram here. Yeah, okay, so now I need to kind of draw the bisectors between the consecutive points, but consecutive is a little bit trickier to define here. But the bisector, say, between S1 and S7 still looks like this. It's the line which is the midpoint in between these, right? And I can do this for all of these. And what happens is you get these kind of nice intersections like this, okay? Okay, and okay. Looks like I'm doing pretty good here. I've drawn a bunch of these. This, not perfect, but okay, great. So this is what the Voronoi diagram looks like now. If I were to highlight, this is the Voronoi cell, right? So this is the Voronoi cell of S3, right? This region in here. Okay, that means any point, again, it means for any point X, I know that I'm closer to S3 than I am to so any other point, right? And so I can write this, for instance, as R3 is going to be the set of points X in RD such that phi of S of X equals S3. Okay, so the set of all the points that map to S3. Okay, so this is cool. Okay, so now I'm going to want to run an algorithm where at some step I need to say I've got a set of data points, which I hope are clusters. I hope these are kind of the middle of those clusters, right? And we'll have to kind of try and like choose and design these points that are the middle of the clusters. And I'm going to want to determine for every point which of the sites it is mapping to, right? So I'm going to choose which of the sites it's mapping to, and so I need to basically resolve for every point X which cell it's in the Voronoi diagram. That's what I need to do. Okay, and so from like this seems nice from a data structure point of view. If I can pre-compute this, this like Voronoi diagram, and in fact it has a lot of nice structure. You can define these edges, you can define these vertices. Like this vertex here is such that if I draw a circle around it, these 3 points are equidistant from this circle here. There's a lot of nice geometry, right? It's where the bisector lines intersect of those, all pairs of those things, right? So I can construct this, and it turns out if you can pre-construct the complexity of this, I can describe the Voronoi diagram in kind of a O of K space in R2, right? So if I have K sites, I can describe this in linear amount of space. Okay, it turns out the number of, you could have n choose 2 lines here, right? Every bisector might be described by 2 points, but you don't get all of them. There are points far apart. S8 and S4 don't have a bisector. So in 2 dimensions, the graph, this doesn't grow too big. And there aren't too many vertices either. They grow linearly with the number of points. It's a very nice property. And in fact, I can build a data structure on top of here, and given a query by using tricks like binary search, I can find the closest site. I can solve phi of S X in, like, if you've taken a algorithm and data structure class, log or K time, right? So in log K time, O of log K time, using kind of binary search in a clever way, I can find the closest point, just like I would in 1D. You should probably be able to see how to do this. I could solve in logarithmic time the closest point. I build a binary tree and I search in the binary tree for the closest 2 things, and then I check those 2 things, right? I can do something similar here. Okay. But this only works in one, yeah, question.
So do you search it? I have a question. Fine.
Yeah, okay, yeah, so I'm not gonna get into the algorithm, how to do this. If you actually take the computational geometry class, maybe this is covered in there, in fact. Okay, great. Yeah, so this is kind of a computational geometry trick. Okay, the downside of this is if I go to higher dimensions, this stops working. Okay. So Voronoi diagrams, right, which is the structure of this thing which is the structure of the projection function I need for these assignment-based clusterings. the size of them is approximately k to the power d over floor of d over 2. Okay? That means just to describe it, write down all the edges and vertices, and actually their higher dimensional faces and subfaces and stuff grows exponentially in the dimension of the space, just the size of it. And so then that means I don't want to write down, I don't want to build a data structure that grows exponentially in dimension. Okay, so this is an example of what's called the curse of dimensionality. Okay, so there are a lot of algorithms or a lot of structures and properties that when you draw pictures in 2D, everything seems nice and simple, but when you get to higher dimensions, start to become very, very complicated. Okay, and actually one thing about the field of machine learning and data mining and what we'll do in this class is we're navigating you in a way to avoid these sorts of things. There are other approaches we could have taken to model problems and stuff that became exponentially bad as we got into higher dimensions, and we basically just aren't so talking about those approaches because we're talking about approaches which are easy and work and what everyone uses. But there's a lot of ways you could try and approach problems that get exponentially bad if you get into high dimensions. And so this is just one example of this. Yeah.
So increasing dimensionality, does it like get exponentially worse as you increase, or is it just like you move that out?
Well, in 3 dimensions, the structure is going to be roughly k squared. 4 dimensions, it's still only k squared, okay. But 5 dimensions is k cubed, right? So you'll deal, like I work with data that's like in hundreds of dimensions, and it's like, it's not so like fathomable to try and construct these things. I've got some friends who kind of they did their PhD thesis on trying to extend things like Voronoi diagrams and structures like that into somewhat higher dimensions. And they did a lot of tricks, and they're like, well, we can maybe get up to like 7 or 8 dimensions, and on some nice data sets, so we can get something that is almost the right answer and at 7 or 8 dimensions, but not like dozens of dimensions. It's not going to work. It's just the size of the structures are so much bigger in your data set, they fill up your hard drives super quickly. It's not the right way to approach the problem, right? And so kind of there's a bunch of road bumps and kind of pitfalls along the way in data analysis, and this is one of them, right? So this is something people have studied. A lot of mathematicians have studied these Voronoi diagrams in higher dimensions. There's lots of cool math behind them, but they're not very useful in higher dimensions. They're useful for thinking about what's going on, right? This is exactly this phi of s function that we need to work with, okay? But what we want to do is to compute phi of s for x a bunch of times. So remember, this is argmin sj in s of x minus sj. Okay, so I just want to compute this function. Well, the reason I thought this was nice is because I could I could solve this in logarithmic time very quickly. I could look up the right answer. Actually, I could do projection for doing dimensionality reduction basically in constant time if the dimension is constant, right? I take dot products, right? So it's basically linear in the dimension. This is logarithmic, but independent of the size of the data. This is basically log k. So this is, but I can compute this. Well, it's an argmin, right? So I can just say, well, set S star equals S1, and then for J equals 2 to K, if X minus Sj is less than X minus S star, then set S star equals to Sj. Okay, I can do this for loop, and so I can just find the optimal projection this way. This is linear time. This is O of K time to run this. It's not so bad, but it doesn't have kind of the nice geometric structure. I can't exploit the nice geometric structure anymore. And so the algorithms are actually, we're going to be able to say a lot less about how well the algorithms actually work. I can do this, so I can just compute it. I can brute force it. And it's not so bad. And so we're going to do this instead, but we're not going to be able to, we're going to have, there's going to be a lot of weird things that can happen because of this. If you go back, we're going to run something like a gradient descent algorithm. We're going to iteratively get better and closer, but it's not going to be so convex. I'm going to have to rely on these other things, and I'm not going to have convexity. And so so we won't be able to say much about how well it actually works. Okay, but I'll say something, and I'll give you some insight into that. Okay, let me just write up one more thing here again, is that we're going to look at, so in general, assignment-based, so clustering. Okay, and we're going to find, so X is a subset of RD. S is going to be, the size of S is going to be equal to K, and we're going to find, so the K-means problem is going to be S star equals R min of S such that S is equal to K, which is sum I equals 1 to N of Xi minus phi of S Xi squared. Okay, so this is the K-means formulation. And so you see it relies on this phi function here, but there are other formulations here where we're going to say arg, and you see this gives a cost function. One clustering is better than the other, but I can do other cost functions here where I can say max, arg, yeah, I can say max of Xi in X of Xi minus phi of S Xi. Or I can say I want to minimize the furthest point mapping. That takes the max there. That's the K center formulation. The K median formulation is arg min S equals K. And again is going to be a sum, I equals 1 to N. But now I look at Xi minus phi of S Xi. This needed absolute values here. Yeah, absolute values. Okay, so now I'm just minimizing the sum of the distances, not the sum of the squared distances. That's called the K median formulation. This one is somehow like, it's more stable, it's more robust outliers, but as we'll see, it's much harder to actually work with. The K-means formulation, the sum of the squared errors, there's going to be a fairly simple procedure which is going to work pretty well, and that's going to be much harder in this case. That seems maybe more natural, but it's not going to be kind of have the strongly convex component to it. And so this one will be harder to solve for. So we'll mostly look at the K-means, and we'll talk about how do we find that subset S that minimizes this. Okay, so that's what we'll talk about next week on Tuesday. So great. Okay, we'll stop here, and the quiz should now be open on Canvas. So again, you're welcome to stay on Zoom or in the classroom. Recommended take it. We'll be around to answer some questions.